I will give you a presentation about how you can increase energy efficiency in machines by model-based design. As Paul already told you, in Flanders we have a new research organization, Flanders Make. We have been started up last year, so now we are more or less existing for one year. And what is Flanders Make? It is a strategic research center for the manufacturing industry in Flanders. We are building further on two existing research institutes, Flanders Mechatronics Technology Center, which was working for the machine building industry in Flanders, and another research institute, Flanders Drive, which was working for the automotive industry in Flanders. In Flanders Make, we are also working together with the universities, so we are working together with research labs from the 5 big universities in Flanders. What do we want to do? We want to bridge, in fact, the gap that exists between research at the universities and the applications in industry. So we as a research center try to be that bridge between those two domains. What is our mission? So we want to strengthen the long-term international competitiveness of the Flemish machine manufacturing industry by carrying out excellent industry-driven pre-competitive research, and we are active in 3 technology domains. We are working in the domain of mechatronics, in the domain of product development methods, and in the domain of advanced manufacturing technologies. We are also focusing on 3 application domains: application domain of the machines, application domain of vehicles, and then also application domain of factories. We have 8 research programs. You can see them over here. Today, I will mainly talk about 2 of these research programs. We have one research program focusing on clean and energy efficient motion systems, and then another research program on intelligent product design methods, in fact, model-based product design methods. And in this talk, I will show how you can use the innovative product design methods, the model-based product design methods, in order to increase the energy efficiency of motion systems. This is an overview of my presentation. I will start with a short introduction about the importance of energy efficiency, and then I will give you 2 examples on how we used model-based design to increase the energy efficiency in machines. And then finally, I will end with a summary and some conclusions. So the introduction. As you all know, energy efficiency becomes more and more important when designing a machine. And the reason of that is twofold. On the one hand, because there is an increased societal awareness about the importance of energy efficiency. People, they want to be green. Also, they want to have green machines. Also, the legislation is becoming more and more stringent with respect to energy efficiency. And also from an economic point of view, energy efficiency is becoming quite important because of the increasing prices for energy, as you can see here also in this graph here. So you see that the price for a barrel is significantly increasing. And as a result of that, also the manufacturers of machines are taking into account much more energy efficiency into account in the design of new machines. If you want to reduce energy consumption during the use phase of a machine, then you have typically a general approach which is being followed. First of all, you try to avoid useless energy consumption. So, for example, when a machine is in standby, then you have to turn off the machine. On the other hand, there are inevitable losses in some functional components, which are always there, and you want to decrease these energy consumption in these functional components. And then if a process is generating energy, you can also try to recuperate that energy. For example, braking energy or waste heat recovery in machines is a potential source for energy recuperation. We have been applying this approach to the drivelines of production machines and vehicles, and we have been looking at 2 levels. You can first look at component level. You can try to minimize the energy efficiency of certain components, and a lot of companies are doing this already. On the other hand, You can also gain a lot when you are trying to look at a system from a system level point of view. So considering all the interactions between all the different components, and in this way you can also trying to increase the energy efficiency. So you have to look at the system as a whole. There will be energy flowing from one component to another component, and by taking that into account in the design, you can also decrease the energy consumption. So, for that energy, to increase that energy efficiency in the design of the machines, we are using a model-based design approach. So what will this model-based design approach offer us? So it will offer us the opportunity to quickly evaluate the impact of design changes. So you can typically in model-based design you will use a model to describe the function of the components. So you will start with modeling different components, then you will combine the component, and then you will simulate the whole machine. What is the difficulty with energy is that energy is flowing in between the different components, so therefore you need system-level models of your machine. So you cannot look individually at different components, you have to look at the whole of the different interacting components. And we are using 1D simulation software that is existing, and we are looking at Flanders Make, how you can use those available softwares to increase the energy efficiency in the design phase of a machine. A first case study that I will talk about is a hydrostatic drivetrain, and we have been looking at these hydrostatic drivetrains and at their energy efficiency. We have some member companies. For example, we have a manufacturer of harvesting machines, which also gave a presentation before noon. And in these harvesting machines, they have such a hydrostatic drivetrain. Such a hydrostatic drivetrain consists of a driving motor, which is driving a pump, and then this pump is driving in parallel two hydro motors. And then each hydro motor can drive a wheel of the vehicle. What is the advantage of such a hydrostatic drivetrain? That you, by changing the strokes of the pump and the hydro motor, you can change the transmission ratio between, on the one hand, the motor, and on the other hand, the load. We built in our lab an experimental setup, an experimental hydrostatic drivetrain setup, where an electromotor is driving a pump. This pump is driving in parallel through two hydro motors, and then we have also a simulation of the vehicle load. We have a flywheel here, and we have an electromotor here. And then we asked ourselves the question, we would like to increase the energy efficiency of this setup. And we want to add an energy storage element in this setup, and we want to evaluate which energy storage element would be the best. And therefore, we are thinking of different possible concepts. On the one hand, we could add an energy storage component in the mechanical domain, for example, by adding a flywheel to the system. We could add energy storage in the electrical domain, for example, adding supercapacitors or batteries connecting to the DC bus of the drive of the system. Or we could add energy storage in the hydraulic domain by adding hydraulic accumulators to the system. And the question was, what is now the best? We wanted to use model-based design, or wanted to use models to give us an indication about what was the best solution for this problem. So therefore, we first built a model of the initial drivetrain consisting of the driving motor, a model of the driving motor, a model of the pump, the hydraulic circuit, the hydro motor, and the load. We had done this model, and then a second step was the identification of the different parts of this model. So we were measuring the efficiency curves of the different components, and we added these efficiencies into the different components. So we had initially the ideal behavior, and then we extended this ideal behavior of the different components with some energy efficiency characteristics. And then a final step was to also add the energy storage components to the models. So we have added here, for example, a model of the accumulators and the valves which are connecting these accumulators to the hydraulic circuit of the hydrostat. We did this not only for the hydraulic components, we also did it for the electrical storage elements, and we did it also for the mechanical storage elements. Then the next step was we wanted to evaluate how good the different energy storage mechanisms were, and therefore we were doing some simulations of some representative load scenarios of the system. And an important step was that we had to dimension the different energy storage components. So we had to choose an optimal volume of the hydraulic accumulators. We had to choose an optimal size, for example, of the supercapacitors. So we were changing the number of capacitors per serial branch and also the number of parallel branches. And in this way, you could see how this was influencing the total cost of ownership of the machine. The more energy storage you foresee, the higher that the cost will be, but also the higher the energy efficiency probably of your system. And that's what you can see here in this graph. So you had here a certain optimal number of serial and parallel branches of the supercapacitor. We did the same also for the accumulator. And then we could compare, using this model-based, using these models, we could compare the total cost of ownership of the different energy storage elements. And if you see here, when you have no hybrid solution, no energy storage element, then you could gain already a certain cost when using an electrical storage element, and even more when using an hydraulic storage element. And then we were wondering, why is this the case? And also, therefore, we could use the models, and the reason, in fact, was that when you are trying to recuperate braking energy, this braking energy is typically here at the load side. If you want to use electrical components to store your energy, then the energy has to flow through the hydromotors, through the pump, through the electromotor, and here you have your energy storage element. And if you want to reuse then that energy, it has to pass again through the electromotor, through the pump, through the hydromotors, and then you could reuse it at the load side. So, and each of these components has a certain energy efficiency and resulting losses. So you have loss in all these components, and when you have an hydraulic storage element, you only have to pass through the hydromotor, and then you're already at your storage element, and in this way you have less losses. So this was the first example. Then here we mainly focused on the design, and then I have a second example where we focused on the control of a system. So by improving the control and using a model-based controller, you can also improve the energy efficiency of a system. And we applied this to our badminton robot. We at Flanders Make, we developed a badminton robot. What was the reason? That was, we wanted to develop our own machine, and we have chosen a badminton playing robot. Why a badminton playing robot? Because badminton is a very high dynamic sport, and also the machines that our member companies are developing are also high dynamic machines, and therefore we have chosen the application of playing badminton. The badminton robot, how is it built up? It consists of a linear motor, and then also two rotational motors, one to position the racket and one to hit with the racket. So that's what you can see here. You have here the linear guide, and then here also two rotational motors. And here you see a picture or photo of our robot. Initially, we had this robot, and it consumed quite a lot of energy. And we were wondering, okay, how can we increase the energy efficiency of our badminton robot? And the first guess was that our badminton robot, it was accelerating quite a lot and also decelerating quite a lot. And we thought that during the deceleration of the robot, a lot of energy was consumed in braking energy, was burned in the braking resistors in the electrical part of the drivetrain. So we thought, okay, maybe we should add some capacitors in the drivetrain, in the electric part of the drivetrain. And in this way, we would expect that we could store the energy in these capacitors, and we would expect that the energy efficiency of our machine would drastically increase. However, we did this, and then we saw, okay, there's almost no energy efficiency increase. We only had a reduction in energy consumption of less than 5%. And then we thought, okay, maybe we have to do a more thorough analysis of what is the reason for this, and trying to use this analysis to further increase the energy efficiency of our robot. Therefore, we developed models of the badminton robot, both of the electrical part of the robot and of the mechanical part of the robot. We had, for example, elements of the brake resistance, the coil resistance. We also had elements which were representing the friction in the mechanical domain. So we were modeling both the electrical domain, the electrical drivetrain of the robot, as well as the mechanical part of the drivetrain of the robot. And then we were also doing a system identification where we were trying to find the real parameters of all the parameters in the model. And then we could do an energy analysis. If you look at this graph here, all the losses are shown. You can see in this graph how much energy is only consumed in the braking resistors. And it was only a very small amount of the power, or the consumed power, of the consumed energy that is consumed in these braking resistances. And this explained why we could only achieve a limited energy efficiency reduction or increase by adding the supercapacitors. And therefore, if you further look at this graph, you can see that a lot of energy is consumed in friction energy, and also a lot of energy is consumed in the motor due to the copper losses that are there. The friction losses, they were mainly related to the speed with which the robot was moving, while the copper losses, they were mainly related to the acceleration. So the higher the acceleration, the higher the copper losses, the higher the speed of the motor, the higher the friction losses. And therefore, we decided to change our control strategy. And because initially we had a control strategy where the robot was moving as fast as possible to the point where it had to intercept the shuttle. So if you're going back to this graph, so we have two cameras at the back of behind the player, which were monitoring the shuttle. So the shuttle is monitored. And in this way, we could predict the trajectory of the shuttle, and we could see to which position the robot has to move in order to be able to hit back that shuttle. The first controller that we developed, then the robot was moving as fast as possible to the position where it had to hit back the shuttle, and then it was waiting for a certain amount of time, and then it hit back the shuttle. Therefore, and then in this way, it was really accelerating very hard, moving with a very high speed, and then decelerating also very abruptly. And in this way, consuming a lot of energy. We decided to change that control strategy and to change it into a just-in-time controller, where the robot was accelerating with a lower acceleration, was moving also with a lower speed, and was decelerating also in a smoother way. You can see the results here. We were able in this way, based on the simulations, to reduce more than 90% of the losses. So in the simulations, we really had a just-in-time controller. In the real controller, we had to allow a little bit more robustness. But actually, we still could get more than 50% of energy reduction by just using the control strategy. Just by having the same hardware, the same performance, we were able to hit back the same amount of shuttles. But just by changing the control strategy, having the same performance, we could reduce the energy consumption with more than 50%. I have here also two videos. So first video is showing the performance of the original controller, and you will see that the robot is moving to a certain position and is then waiting, and then is hitting back the shuttle. So you will see it. So it's moving, waiting, and playing back. And then I have a second movie where the robot is moving much more smoothly. So it is moving gradually to the position where it has to hit back the shuttle, and is then hitting back the shuttle. So we have the same performance in both cases. The same amount of shuttles is being hit back, but the energy consumption has been reduced by more than 50%. Okay. These were two applications that we studied and investigated in our lab. However, we used the same techniques also in some industrial applications. For example, here you can see a crane, and in this crane, you can see here we have such a drivetrain. We have a diesel engine, and this diesel engine is driving a generator, and then this generator is then driving a few motors. And there, the question of our partner was, what kind of energy storage element should I add, and which kind of control strategy should I use? So in this case, we also used models, and it appeared the best to add some supercapacitors to this system. And we also developed in this case an optimal control strategy based on the developed models of this system. And then you could see that by adding the energy storage elements, you would have a payback time of 2 to 3 years before you would gain back the investment of the cost of adding the energy storage element to this system. And after 2 to 3 years, you would gain quite a lot. So here we use the same design techniques and the same control design techniques, model-based design techniques, model-based control techniques to evaluate the energy efficiency of this system. This brings me to the conclusions of my talk. So the motivation of the talk is that energy reduction in machines, in vehicles, is really necessary because of environmental and economic reasons. And if you want to evaluate the energy efficiency, the energy consumption in a machine, in a vehicle thoroughly, you need models, you need 1D simulation models, because you have to take into account the total system. You cannot start focusing on a certain component. No, you have to focus on the interaction between all the components. So you need system models. And using these system models, this will allow you to optimize the energy efficiency of the designed machines and vehicles. Thank you for your attention.